Welcome to Unit 8, Lines and Planes, Lesson 5, the intersections of lines and planes. The warm-up I'll leave to you. If you want to see solutions to the warm-up, they're available on the class website. But we're going to continue on. This is basically from Lesson 4. All right. So we're going to continue on here with how lines and planes can intersect. There's three cases. Case 1, the line and the plane intersect at a point. So they're exactly one solution, and of course that solution would be right here, point P. There we go. Case 2, the line lies on the plane, so that every point on the line intersects the plane. So of course anything on this guy right here is a solution, and so of course there are infinite solutions. And then finally, case 3, the line is parallel to the plane. The line and the plane do not intersect, so here there's no solutions. You can see that here this red line here is running parallel to this plane, and that line is distinct from the plane, so again it never hits, never intersects. Alright, how do we actually solve it, Mr. Wills? So here's my line, L1, and my plane, pi1. So to do to find if they intersect, the first thing I'm going to do is put it in parametric form. There's my parametric form. I'm going to cheat a little bit there. And what do I do here? I take this and I put this into a plane. So I'm going to have 4 bracket 3 plus t minus 2 bracket 1 minus 4t, and then I'm going to have minus, and then 2 minus 8t minus 8 equals 0. So here I get 12 plus 4t minus 2 plus 8t minus 2 plus 8t minus 8 equals 0. If I add up the like terms here, I get 20t is equal to 0, so that means t is equal to 0. What does that mean? Well, I take this, put it back into line 1, and if I do this, in line 1, I get this. I get x, y, z is equal to 3, 1, 2 plus 0, 1, negative 4, and negative 8. So here my POI will be 3, 1, 2. So this is the point of intersection between the line and the plane. POI between line 1 and plane 1. Alright, here's the next example. Next example is this. So again, already in parametric form. So again, I'm going to substitute line 1 into plane 1. So here we go. I am going to have 2 bracket 2 plus t minus 5 bracket 2 plus 2t plus bracket 9 plus 8t minus 6 equals 0. So this is going to give me 4 plus 2t minus 10 minus 10t plus 9 plus 8t minus 6 equals 0. You're going to see here that 2t minus 10t plus 8t is 0t. But on the other side, I'm going to have, gives me 3 if I bring all my constants to the right side. Of course, this is never a true statement. What does that mean? Therefore, line 1 and plane 1 do not intersect. So that means there is no solution. Okay, how can I do this without actually solving? So here, without solving, determine if each line intersects. So, helpful hint. If the normal of the plane and the direction vector of the plane are Perpendicular to the line on the plane must then be, because the normal is perpendicular to the plane and the direction vector is parallel to the plane, that means that the line and plane must be, whoops, parallel. Let's try this again. Alright, and can either be two options here. They can either be coincident, which means there's infinite points of intersection, the line is on the plane, or distinct, that means there's no point of intersection, they are separate. So here, let's look at this. So here I can see my direction vector of my line is 2, 3, negative 1. My normal of my plane here is 4, negative 1, 5. So my normal dotted with my direction vector. If I do this here, I'm going to get 8 minus 3 minus 5, which gives me 0. So the direction vector dotted with normal gives me 0. That means that L1 is parallel to plane 1. So how can I tell? Are they coincident or distinct? So what I'm going to do is I'm going to take a point from line 1, and I'm going to put it into the plane. Why would I do this? Because if the point from line 1 is on the plane, then that means they are coincident. If it is not on the plane, that means they're distinct. So my point from line 1, this would be from the parametric equation, 1, negative 1, negative 1, and I'm going to put it into 4x minus y plus 5z plus 2 equals 0. A little bit of space here. So I'm going to have 4 times 1 minus negative 1 plus 5 times negative 1 plus 2 equals 0. So 4 plus 1 is 5, plus 5 minus 5 plus 2. So here I get 2 is equal to 0, which of course is not true. That means that the case I have here is distinct to no point of intersection. Therefore, line 1 and plane 1 do not intersect. So, what does that mean? No solution. Alright, here we go. Line 1 and plane 1 again. If the normal of the plane and the direction vector of the plane are not perpendicular, that means there is one point of intersection. So here, again, I'm going to look at my direction vector. My direction vector, or my M, is right here. And my normal is 1, negative 5, negative 7. So I'm going to dot them together. And here you get 4 times 1 is 4. Negative 3 times negative 5 is 15. And then 5 times negative 7 is minus 35. And so this is going to give me negative 16, which of course is not equal to 0. So that means that, therefore, L1 is not parallel to plane 1. That means there is no point of, whoops, that's not the case. That means that there is, my apologies, one point of intersection. All right. So that's a quick way of telling by using the dot product to tell whether there's one point of intersection, infinite point of intersections, or no point of intersection, of course. If they are parallel, then you've got to take the point from line 1 into plane 1. All right, distance from a point to a plane. So to find the distance between a point and a plane, you want to first check if the point is on the plane. So if that is, then of course the distance is not written there, but the distance would be 0. If the point is on the plane, choose any point on the plane Q. Intercept is always an easy one, and then find the position vector from the point to the point on the plane, PQ, and then determine the magnitude of PQ onto the end of the normal of the plane. So let's try the first one first. So step 1, we are going to plug in our point into our plane. So I'm going to have 4 bracket 4 plus 2 bracket 1 plus negative 2 minus 16 equals 0. If I do this, 16 plus 2 minus 16, well, this gives me 0 equals 0. What does that mean? Therefore, 4, 1, negative 2 is on the plane. What does that mean? That means that the distance between um, 4, 1, negative 2 in the plane is 0. All right, that was easy. Let's try the second one. Second one, again, step 1, check to see if it's in the plane. So here I'm going to have 4 bracket 1 plus 2 bracket 2 plus 9 minus 16 equals 0. So here I get 4 plus 4 is 8 plus 9, 17 minus 16, so that's 1 is equal to 0, which of course is not true. So that means the point is not on the plane, so I can go to step 2. Step 2. If the point is not on the plane, choose any point Q on the plane. So here my point Q. So for point Q, I'm going to choose an x-intercept. You can choose any intercept you want or any point that you want. So x-intercept, so my x-intercept will be 4x. Y and z are 0, so minus 16 equals 0. So here I get x is equal to 4. So that means I've got the point 4, 0, 0, and that's my point Q. I'll call this guy my point P, that guy there. So step 3, I want to find that position vector PQ. So PQ, so I'm going to have 4 minus 1 is 3, 0 minus 2 is negative 2, and 0 minus 9 is negative 9. So there's my direction vector PQ. Again, Q here, my point P is 1, 2, 9. My point Q is 4, 0, 0. Okay, that's step 3. Step 4, I'm going to find the projection, the magnitude of the projection. Here he is back again, of PQ onto the normal. That's magnitude. So what's that equal to? That is equal to P dot N, magnitude of that, over the magnitude of my normal. All right. Now again, my normal here is, if I just go up, sorry, my normal of this plane is 4, 2, 1. So here we go. So this is going to be equal to 4, 2, 1, if I remember that. magnitude of 3, negative 2, negative 9, dotted with 4, 2, 1. All over magnitude of my normal. So it's going to be, don't need those brackets around it. It's going to be the square root of 4 squared plus 2 squared plus 1 squared. So here I'm going to have, the numerator will be 12 minus 4 minus 9, the magnitude of that, all over, that's going to be square root of 21. So that's going to be equal to 1 over the square root of 21, which is a very small number, which is approximately equal, just put this in my calculator, it's approximately equal to 0.22 units. So the distance between my point P and my plane is about 0.22 units. You can also tell that they're going to be close by looking at this guy here. You can see that these numbers are really close, so that means that the distance is going to be pretty small. The further away these numbers are from step 1, the bigger you're going to expect your distance between the plane and the point. Alright, the last two examples I have here are just random examples that, well, you can do. This really goes back to, I believe, lesson 2 or 3. We'll do it quickly. Write an equation of a plane that contains the points P and Q and is parallel to the line. So if I know, I can use one of these as my point on my plane, P and Q, but I do know that PQ is equal to a direction vector on my plane. So I'm going to find it. So that's going to be equal to, find my direction vector here, 4 minus 2 is 2, 2 minus negative 3 is 5, and then negative 5 minus 6 is negative 11. So I'm going to use that as a direction vector, and parallel to the line, so I can use this guy here as my other direction vector, M2. So, and I can use either P or Q as a point on my plane. So this one's done pretty quickly. X, Y, Z is equal to, again, it doesn't matter which point I use, I'm going to use point P. So I'm going to have 2, negative 3, and 6, plus T, whoops, 2, 5, negative 11, again, that's just my direction vector PQ, plus S, my second direction vector, which is this guy, 1, 2, negative 3, and there's my direction of my plane, or there's my equation of my plane. The one thing I do need to check though is that the direction vectors here and here not are scalars, and clearly 1 times 2 is 2, but 2 times 2 is not 5. So they're not scalars, and we're good to go. Alright, last example, here we go. Determine the value of k such that this cross this gives me this. Well, let's write it down. So again, we're going to use a cross product here. So I'm going to do it as 3, 7, negative 2, 3, 7, negative 2, and then here I'm going to have A, 3B, A, 3B, and I'm going to cross them, so here we go. That's going to give me 7B, and then this is going to be plus 6 if I go up this way. The next one's going to be negative 2A, and this is going to be minus 3B. And then the last one here is this, 9 minus 7A. And there we go. So that's the cross product of these two. Gives me this. But I know it's equal to, I know this is equal to negative 1, K, and 5. So I know these two things are equal. I know these two things are equal. And I also know these two things are equal. Whoops. So let's talk about the x's first. So I'm going to go with the x's, the x coordinates. So here I know that 7b plus 6 equals negative 1. Bring that 6 over, divide both sides by 7 here, so b is equal to negative 1. Alright, this one has too many variables. I got a, b, and k, but I will go with my z. I know z here is equal to 9 minus 7a is equal to 5. Bring that 9 over, so 7a is equal to negative 4. So a is equal to 4 over 7. So I've got my a, I've got my b. So I'm going to substitute that into the y. So finally I'm going to do y. So y, I'm going to have negative 2 times 4 over 7. Not a nice fraction, but we'll deal with it. Minus 3 times negative 1 is equal to k. So do this quickly. Here I get negative 8 over 7 plus 3 is equal to k. And if I put this in my calculator, I get k is equal to negative 13 over 7. And there we go. And that was the last example done rather quickly. Again, 4 and 5 are not really related to the lesson, but just kind of nice thinking type problems. Well, 4 is not really thinking, but this is a little more thinking here. You could argue this could be really done in Unit 7, and it probably could, but there we go.